last couple of things I want to talk about are defective matrices and the Jordan canonical form. So let's define what a defective matrix is. So we know a matrix A, that's n by n, is diagonalizable if you can write the matrix A in this form. For some invertible matrix X and some diagonal matrix D. Now, if you can't put this matrix, if you can't put A in this type of form, it's not diagonalizable. We also know that A is diagonalizable if and only if there exists n linearly independent eigenvectors. And that's true if and only if the geometric multiplicity for lambda I is equal to the algebraic multiplicity for lambda I for all I. So if there's k eigenvalues, then for lambda 1, lambda 2, all the way to lambda k, the geometric multiplicity has to be equal to the algebraic multiplicity for the matrix A to be diagonalizable. So that means A is not diagonalizable if and only if there are less than n linearly independent eigenvectors. And that's true if and only if the geometric multiplicity does not equal the algebraic multiplicity for at least one eigenvalue. So when a matrix is not diagonalizable, we call that matrix defective. So we can't put it in this form, A is equal to x dx inverse. This just doesn't exist. There's no x you can find that's invertible in a diagonal matrix that when you multiply x dx inverse, you get A. However, we can come up with a matrix J, and we can find a matrix X for any defective matrix where we have xj x inverse and J is almost diagonal. An almost diagonal matrix. So, however, there exists a invertible matrix X and a almost diagonal matrix J such that A is equal to xj x inverse. And this is true for all defective matrices. And it's true for diagonalizable matrices. The matrix J is going to be a diagonal matrix if the matrix is diagonalizable. So what do I mean by almost diagonal? Well, we need to define something called Jordan blocks. So Jordan blocks look like this. I'm going to give you a few examples. Let me give you 4. Let me do a better job with this one. Okay, so a Jordan block is a block that has eigenvalues along the diagonal and ones along this off diagonal. The diagonal that's just above the normal diagonal. We call that the off diagonal. You can even call it the upper off diagonal because this could be a off diagonal as well. So here, this is a 1 by 1 Jordan block. It's just an eigenvalue. And this is a 2 by 2 Jordan block, a 3 by 3 Jordan block, and a 4 by 4 Jordan block. So when a matrix is diagonalizable, it's going to consist of n Jordan blocks. So if the matrix A is n by n, it's going to have n Jordan blocks. So you can write the matrix A as x d x inverse, which is going to be the matrix xj x inverse, where J looks like this, where all of these are 1 by 1 matrices. So this is the Jordan canonical form for the matrix A when it's diagonalizable. Now if a matrix is not diagonalizable, it can have, now of course you can have a 5 by 5 Jordan block and so on, but it's going to have multiples of these types of blocks. So the matrix A, if it's not diagonalizable, what it's going to look like is something like this. Let's put letter M here. So it might have several Jordan blocks, but these Jordan blocks could be of different sizes. It depends on what size this matrix A is, but it could look something like this. So you have an eigenvalue here. Let me clean this up so I can just try this again. Let's say we have 5 numbers here. So this would be J1, and this would be J2. So here I have a 3 by 3 Jordan block, and here I have a 2 by 2 Jordan block, and so we can kind of think of these as like entries in a 2 by 2 matrix. These are just block matrices, and you can see these block matrices look like a diagonal matrix when we put them all together as blocks like this. You could have something instead. You could have let's put a 0 here. Let's put a 1 here. Leave that one alone. Like this. And if you look at this, this is a Jordan block, this is a Jordan block, and this is a Jordan block. So now we have something that looks like J1, 0, 0, 0, J2, 0, 0, 0, J3, where J3 is a 1 by 1 Jordan block, and J1 and J2 are 2 by 2 Jordan blocks. You could also have there's just so many different ways to do this, but here we just have one Jordan block. So this would just look like this. Yeah, so there's many options. You could do these three and put a 0 here, and then you would have 3 Jordan blocks. One that is like this. Oh, so that would be a 4x4 Jordan block, and then if you didn't have anything here. Yeah, so there's lots of different things you can do. So we're going to try to figure out for a particular matrix, I don't think I told you any matrix yet, the Jordan blocks. Okay, so the matrix I'm going to give you is, let's call this A. This matrix is 2, 0, 0, 0, 4, 0, 1, 0, 2. I claim that this matrix is defective, which seems a little strange because this is a lower triangular matrix and it's almost diagonal. The only thing wrong with it is we have an entry right here. So you would think that you would be able to write it as x times d times x inverse, where d is a diagonal matrix, but you actually can't do it. And how we're going to show it's defective, we're just going to show that the algebraic multiplicity of one of the eigenvalues is not equal to the geometric multiplicity. And then from there, I'm going to show you how to find the Jordan blocks and to make this, put this in Jordan canonical form. Let me write that out. So we're going to find the Jordan canonical form, which some people call it the Jordan normal form. Okay, let's get started. So I'm going to find the characteristic polynomial. The characteristic polynomial is the determinant of a minus lambda I, which is actually really easy to calculate because this is a lower triangular matrix. So 2 minus lambda 0, 0, 0, 4 minus lambda 0, 1, 0, 2 minus lambda. Since it's lower triangular, the determinant is just the product of the diagonal entries. Yeah, the diagonal entries, which is 2 minus lambda, 4 minus lambda, 2 minus lambda. I'm going to factor out a negative from each one of these and bring it out. If I do that, I'll get lambda minus 4 times lambda minus 2 squared. And then a negative because I have a negative 1, negative 1, negative 1. You can see that the eigenvalues are lambda is equal to 4, which has an algebraic multiplicity of 1, and lambda is equal to 2, which has an algebraic multiplicity of 2. To show that this matrix is defective, we only need to show that the geometric multiplicity is equal to 1 for this eigenvalue. Okay? So we need to find the eigenspaces. Let's start with the 4 eigenspace. That is the null space of A minus 4 times the identity. Let's find this matrix here. Well, we're just going to plug in 4 for lambda. You can see this becomes a 0 and these two become negative 2. So we get negative 2, 0, 0, 0, 0, 0, 1, 0, negative 2. Now I'm going to put this in reduced row echelon form. All I need to do is divide this by a negative 2. I can move this row of zeros to the bottom and subtract this row from this one. I get 0, 0, negative 2, but I can divide that by negative 2 and I get 1. So then to find the null space, I make this augmented matrix. All of this should be review, so I'm not really going through it too much. We see that x1 is 0, x3 is 0, and x2 is free. So since it's free, we can give it a letter, like S. So you see that the null space consists of vectors that look like 0, S, 0. So this is just the vector E2. So this eigenspace is the span of 0, 1, 0. Okay? Which makes sense because the algebraic multiplicity is 1, and that's the same as the geometric multiplicity. Okay, let's find the other eigenspace. And get rid of this stuff so we can keep it all together. So the other eigenvalue is 2, so I'm going to take A and subtract 2 times the identity matrix. That means I'm plugging in 2 here. You can see that I get a 0, a 2, and a 0. That should be a 0. Let's just double check I didn't mess up. Okay. And now let's put this in reduced row echelon form. Well, that's easy. Just move the row of zeros to the bottom and divide this by 2. Find the null space. The null space, we are trying, actually, let's leave, sorry about that. We're going to find the null space, so this is 1, 0, 0, 0, 1, 0, 0, 0, 0, make an augmented matrix. We get that x1 is equal to x2, which is 0, and x3 is free. So E2 is equal to the span of 0, 0, 1. Okay. Now that we have this, I'm going to put this closer to E4. And you can see that the algebraic multiplicity, which was 2, is not equal to the geometric multiplicity, which is 1. Okay. Let's keep that. I'm going to say here we have the geometric multiplicity is 1, and here I have the geometric multiplicity is 1. So this matrix is in fact not diagonalizable. All right. Now, this is the interesting parts of the Jordan canonical form. I'm going to talk about it. If you're really interested in this, I would suggest that you look up the Jordan canonical form online, learn about it. You could, I think the book has a supplemental chapter for you to read online. It's not in your book, but it's actually extra chapter that they give you if you purchase the book. I think you can also just find it online somewhere. But they talk about the Jordan canonical form in detail. And yeah, you're going to see this probably in another, like a higher level linear algebra class. So I'm just going to basically just show you a little bit of it, how they figure out the Jordan canonical form, just for this matrix. If you're more interested in it, you can find more details online. Okay, so what we're going to do to find the Jordan canonical form, there's a couple little tricks. The first trick is the sum of the dimensions of the eigenspaces. That is equal to the number of blocks. And then the minimum polynomial, I can't remember if it's called the minimal or the minimum. I think we're gonna call it the minimal polynomial, and I'll tell you what that is in just a minute. That is equal to, that tells us the size of the largest block. Okay. So let me tell you all the possibilities for this Jordan normal form. So our matrix originally was 2, 0, 0, 0, 4, 0, 1, 0, 2. And we're going to write it like this, where J has the eigenvalues on the diagonal. So here's what could happen. Remember, there are 2 eigenvalues and one of them is repeated. The 2 is the one that's repeated. So we could have 2, 2, 4. Or we could have 2, 4, 2. Or we could have 4, 2, 2. Then our options are, we're going to have a 1 here, no 1s, or a 1 here. Now the 1s only appear in between the same eigenvalue. So that's one thing to know about the Jordan normal form. So like right here, because I've separated them all, you wouldn't have any 1s. And if you didn't have any 1s, your Jordan normal form would look like this. But we know that our matrix is not diagonalizable, so this is not an option. So it's going to be one of these. And I think for this particular example, it doesn't matter which one you choose, because you can rearrange the basis vectors in X. But anyway, so this is the idea of how, like, what happens. So the first thing is, if we add up the dimensions of the eigenspaces, which just add up the geometric multiplicities, so we had 1 here and 1 here, so that's 2. That tells us we're going to have 2 Jordan blocks, which makes sense because those are the only 2 options we have. Here I have a Jordan block, and here I have a Jordan block. Okay, so it's one of these. And also, if I find the minimal polynomial, it tells me the size of the largest block. Here, the largest block is going to be a 2 by 2 block. You can see this is a 1 by 1 block, this is a 2 by 2 block. And the minimum polynomial, so the minimal polynomial comes from the characteristic polynomial. The characteristic polynomial in our case was p of lambda is equal to lambda minus 2 squared, lambda minus 4. The minimal polynomial is where you take your actual matrix A, and you have 2 options, lambda minus 2. Okay. Let me show you something real quick. So you can write this as the minimum polynomial is either going to be lambda minus 2 times lambda minus 4, or lambda minus 2 squared times lambda minus 4. So we have to keep the eigenvalues, so that you see how I have a lambda minus 2 squared and a lambda minus 4. So we have to keep all of these eigenvalues in our minimum polynomial, but we can have different powers. So we want to find the smallest power on these factors here, such that when I plug in my matrix A, I get 0. Okay? So you're going to plug in A wherever you see a lambda. And if you get 0, then that is the minimal polynomial. So it turns out that if you plug A into this, so this is A minus 2i, a minus 4i. So if you take a minus 2i and multiply it by a minus 4i, so we've already found these matrices. Remember, we found them using when we were trying to figure out the null space. So plugging in 2 here, we got 0, 2, 0, and then plug in the 4 as well. You'd multiply those two matrices, and if you get 0, that is the minimum polynomial. But it turns out that this is not equal to 0. It's actually only this one is equal to 0. Let me explain this a little bit better. If you have the characteristic polynomial, let's say this is your characteristic polynomial. What are all the options for your minimal polynomial? You could have lambda minus 3, lambda minus 1, lambda plus 3. That's one option. You could have lambda minus 3, lambda minus 1 squared, lambda plus 3. You could have this guy, instead of putting the 2 here, I could put the 2 here. Or I could maybe put a 2 here, or I could put a 3 here, or a 4 here. So something like this. And what I'm going to do is I'm going to plug in the matrix A into each one of these and see which one of them gives me 0, the one with the fewest amount of factors, and that is your minimum polynomial. So for our particular example, when we plugged in A into the only options we could have, which are lambda minus 2 times lambda minus 4, and lambda minus 2 squared and lambda minus 4, the first option doesn't give us 0, so that's not going to be the minimal polynomial. The minimal polynomial is the actual characteristic polynomial for this particular example. And you can see that if we have several eigenvalues with different powers, it can get complicated. So we're not going to do that. We're just looking at one example. Okay, so this is our minimal polynomial, and what we're going to get from this minimal polynomial, which I wrote up here, let me just scroll back up. The minimal polynomial tells us the size of the largest block. So this number here 2, because we have our minimal polynomial, this tells us that we're going to have a 2 by 2 Jordan block. And that's going to be the largest Jordan block we have. And then we have an algebraic multiplicity here of 1, which tells us that the largest Jordan block we're going to have involving this eigenvalue is a 1 by 1 Jordan block. And so you can see from our two options, here's a 2 by 2 Jordan block that involves the eigenvalue 2, and this is a 1 by 1 Jordan block that involves the eigenvalue 4. Okay, so it turns out it doesn't matter which one we use. I'm going to use this one here. And now I'm going to show you how to find the matrix X. Okay? So let's copy this. And move it down. Okay? So let's paste it right here. So I claim that we can take our matrix A, which our original matrix was 2, 0, 0, 0, 4, 0, 1, 0, 2. And I can write it as X times 2, 1, 0, 0, 2, 0, 0, 0, 4, X inverse. But I need to figure out what X is. Since I claim this is true, I can figure out what X is. And this is where it gets really interesting. So you know what the eigenspaces for 2 and 4R. So you need to find a basis. You need to find a vector, v1, v2, and v3, such that you see that this column here, we get that A times v1 is equal to 2v1. This is going to go with v1. Then you want to say that A v2 is equal to v1 plus 2v2, because this 1 corresponds to v1, because this is in the v1 section, so this is v1, v2, v3. So when you plug in v1, you get 2v1. This one is saying when you plug in v2, you get v1 plus 2v2. And then A v3, when you plug that in, you get 4v3. You can do this. How you would do it is, first off, in order to get v1, well, this is just an eigenvector. So you can choose any eigenvector in the 2 eigenspace, which the 2 eigenspace, if you recall, let's move up just to see what it was. The 2 eigenspace is any linear combination of 0, 0, 1. So you can just go with 0, 0, 1. Let me scroll back down. So we can let v1 be 0, 0, 1. And v3, we want it to be an eigenvector of eigenspace, the 4 eigenspace. So v3 is going to be, let me scroll back up, sorry, I can't remember what the eigenspace was. This is 0, 1, 0, so we can use that vector. Scroll back down. This is 0, 1, 0. And then v2, we need to figure out what v2 is, and that's the hardest part. We need to satisfy this equation here, that AV2 is equal to V1 plus 2V2. I can move the V2s to the one side, and I get that A minus 2 times the identity matrix, V2, is equal to V1. And we can say V2 is equal to x1, x2, x3. So all you need to do is subtract 2 times the identity from your matrix A, which we know is, this is a 1, this matrix. And then you want it to equal V1, which V1 is 0, 0, 1. So you can see that x1 is free, x2 is equal to 0, and x3 is equal to 1 for this to work. And if x1 is free, you can just use the vector. Now you want it to be linearly independent from these vectors, because remember x has to have a linearly independent columns. So we can't use 0, 0, 1. You have to use something with a non-zero number for x1. So you can go with 1, 0, 1. Yeah, it's really complicated. But what happens is that now I claim that the matrix A, which we said was 2, 0, 0, 0, 4, 0, 1, 0, 2, is equal to x. So here are my 3 vectors, 0, 0, 1, 1, 0, 1, and this vector, 0, 1, 0. This is my vector x. My Jordan block is 2, 1, 2, 4. And then if I just figure out what the inverse of this is, you can do that calculation. You'll see that if you multiply these 3 matrices together, you'll get this matrix, and this one's almost diagonal. And that's just getting our feet wet when it comes to the Jordan canonical form. Yeah, so There's a lot of information here, and I'm not going to test you on that. I just wanted you to see it and just have an idea of what it is. And that's it. I hope you have a great summer, and maybe I'll see you sometime next semester.